one question that we had was, can you use the same tetrapod formulation or the structure on different material systems, and would that unleash like a whole like range of new applications?
Yeah, basically, we started with tetrapods, and then we have been so successful because we harvest here the material properties plus 3D shape. So the combination, the shape plus properties combination makes them.
Hey everyone, welcome back to the It's a Material World podcast. I'm your co-host Puneet, and David today is battling a cold. And so first of all, just very appreciative of you kind of staying with us and sticking with us with the episode despite the sniffles and everything alongside that. How are you feeling?
Yeah, luckily Zoom has a mute feature, so you don't have to hear me sneeze all the episode. But yeah, just coming back from Europe, just coming out with a little bit of a cold. So, on the up and up, but still a little sick right now. But today was a really cool episode, and I could have used some of what we were talking about, which
Yeah.
is using these smart materials, zinc oxide, and these tetrapod, which is just a structure. And in this structure has very unique properties, and one of them is antiviral. And I think the coolest thing for me about the conversation was that a lot of people we talk to are in the very beginning stages, or they're starting companies, or they're like just trying to get out there. And he has actual product on the market that he sells in Germany. So I think it was very interesting, as he's been in this research field for like 15 years or something like that, and just very knowledgeable. And he's accomplished a lot, which I thought was very telling throughout the conversation.
Yeah, for sure. And it was really cool to see. Typically, you see those early stage innovations happen in the research lab, right? And then maybe it spins off into a startup, but usually maybe there's some corporate partnership that turns it into a product. But for him to be able to create that product was really impressive. And for one thing, just taking a step back, I'm a little bit surprised, maybe I'm jinxing myself, but we were literally together, you and I, for like 7 straight days. So I'm just going to keep my fingers crossed that I don't need this antiviral cream. So yeah, but I think another cool like application of his technology was kind of the flexible electronics. And so basically his research focuses on zinc oxide tetrapods, kind of like imagine a tetrahedron, but their legs or feet, hence the pods. And it was just super cool seeing kind of the effect of that structure, its like self-assembly property, and how that could even potentially be used in other material systems, not just zinc oxide. So yeah, it was just a really cool episode. Smart materials as a whole has always been fascinating to me, how they can respond to external stimuli. And for us to be able to dive into one of those instances and its versatility was very interesting. So before we get into the episode, did you have anything else you wanted to add?
Nope. I just wish I could have had some of that anti-cream earlier.
Yeah, for sure, for sure. So yeah, for our audience, please join our Discord community. It's absolutely free, and we discuss all things material science. You can get your questions answered there. And then if you enjoy the episode, please leave a rating and review on your preferred podcast platform. It means a lot to us, and it really helps us grow.
Metamaterial Inc. is a developer of high-performance functional materials and nanocomposites. Meta delivers previously unachievable performance across a range of applications by inventing, designing, developing, and manufacturing sustainable, highly functional materials. Meta is a fast-growing company with a positive and committed work culture and a phenomenally talented workforce. Our employees are inspired to do exceptional and innovative work and are proud to contribute to the success of the company, and they are our greatest asset. Meta attracts people from all countries and cultures with over 35 spoken languages represented across all our teams. Meta believes that diversity drives creativity and innovation. With locations in Canada, the United States, the UK, and Greece, Meta is growing and is looking for new talented people to join the team. If you're passionate about doing your best work, making a difference, and having fun while doing it, apply to one of our open positions at metamaterial.com/careers.
Hello, everyone. So for today's episode, we are excited to welcome Dr. Yogendra Mishra, current professor of nanomaterials at the University of Southern Denmark. And since earning his PhD in condensed matter and material physics, he has over a decade of research experience. He has recently crossed the 10,000 citation mark with over 270 publications. And today he is joining us to talk about smart materials and their structure-property relationships that make them useful in multiple applications. Congratulations, first and foremost, on the amazing accomplishment, and thank you so much for joining us today.
Yeah, thank you very much for the invitation. I'm very happy to be part of it. Please go ahead.
Amazing. So just to start off, maybe you could define what exactly a smart material is, and then what type of smart materials you focus on in your research.
Yeah, well, as a general smart material, how we define when we sizing down the material from, say, large piece to a small piece, then what happens? The surface goes up and up. And when we talk about a small material in the size range of 1 to 100 nanometer, then it's a much more surface contribution. That's how we define nanotechnology is, because the materials are having very kind of extraordinary properties suitable for many applications. And that's up to some extent, we call them as a smart materials because of these properties. So if we design the main idea is that, first of all, how to design these nanoscale materials, and then the second, how to integrate multiple components together in a way so that we have access to these properties in a very right way. So smart materials means either it is a single component material or it is a multi-component material in the size range of nanoscale regime, and with unique properties which are suitable for different applications. That's how we define smart materials. Basically, our focus of smart materials is that we know that these materials, when they are in this size range, say 1 to 100 nanometer, then they hold very nice properties, but they are too small to use in our daily life applications. We need really complicated technologies, but we are always motivated to design simpler technologies with high performance, so that we are paying less money for the technology and we have much improved response. So we have to think about how to use these nano properties at a kind of at a larger scale in a simple manner. And that's where our research comes into the picture. So we got motivated with the kind of sponge in our kitchen. You see that the sponge is just a plastic material. It's a polymeric material made out of some kind of interconnected network. And these are just fibers connected together. And because of its architecture, you can bend it, you can squeeze the water, you can release the water, and you have many properties. So when you press it and put into the water, it holds the water, and then you can release it. In the same way, we got motivated to design, to arrange nanoscale elements in the kitchen sponge form, so that we can harvest, we can use those nanoscale features on the large scale in a very simple manner, so that we can get their applications in our daily life in a simple and cost-effective manner. So that's how we define our smart material. That is our focus basically. And here the advantage is we can use the nano functions in a very simple manner.
So just to clarify, so the smart material is mainly like define the size of the particles. So a material could be both a smart material and a non-smart material simply based off how large the actual particle size is. Is that correct? Or am I misunderstanding what you're saying by just things in the nanoscale?
No, basically smart materials in the sense that every material, when it is in the size range of nanoscale, then it has unique property.
Gotcha.
And you can say that the material is kind of responding when you put light on it, when we apply voltage on it, then the material is going to respond in a completely different way. And that can be useful for many devices, many applications. I mean, all these devices you see today, mobiles and many other technologies, the weight is going down, the size is going down, the performance is going up and up. So in some way you can say that these devices are made out of smart materials. What we are specifically talking it, so for example, if I have a material which is photocatalytic, but I also want to have electronic feature on the top of it, as one material with more than one properties on board, then we say as a smart materials.
Got it. So yeah, that was kind of how I understood smart materials as being the properties change as a response to external stimuli such as stress or heat, light, etc. So I was just wondering if you could talk more about your specific smart materials. I know you're working in the zinc oxide field, and I know also that the field as a whole believed that kind of this zinc oxide material was figured out. There wasn't really much more left to discover. So can you talk about what inspired you to persevere and continue to work in this field despite kind of the overall research field's beliefs?
Well, so that's a very good question. And I would like to put one line here that I started from a very interior village in India from kerosene lamps, and I have reached to Denmark. So I have seen all those paths in the life. And it has been a self-motivated path thanks to family, teachers, friends, mentors, and everyone on the way. Somehow, this has really helped me a lot to correlate the things from the normal life to my research life in a very good way. I have been very happy. And there is a background story behind that. When I started with working with nanoscale materials, I was always asking a question myself, that these materials are so small, and if I want to really use them, then I always either need a substrate or I need something where this material would need to be mounted, and then we have a lot of limitations. So during 2009, 2010, when I arrived in Germany, I had a freedom to start something new. And at that point, I had the kind of perception from how these popcorns are able to arrange when you go to watch the movie, and when you buy a bucket of popcorn, these popcorns are able to arrange themselves in a very nice way with certain degree of porosity. I was thinking in the same way that if I could make some nanostructures in a loose powder form and then try to put them together, and then it could happen that they will be able to arrange into a network form. And that really worked very, very well. So I started working with zinc oxide material because this material is miraculous material with large degree of freedom in terms of growth of various structures. And thanks, I could develop a process which offers the growth of such complex shaped microstructures. We call them tetrapods. And this gave us really a way how we can make a 3D networks like a sponge out of zinc oxide. So we started from there. This was a recipe developed just by a very simple approach based on kitchen experience. And then what I did, I developed several tetrapods like micro and nano structures, and then I was putting them together. I mean, they have the ability to self-assemble in form of a three-dimensional architecture with random degree of porosity, and that gives us a lot of advantage. And what I did, I took that powder into a kind of, say, hollow cylinder. I pressed a little bit, and then I was putting it into the oven to heat it at high temperature for a longer time. And in this way, I could develop a network out of these tetrapods, which was behaving like a sponge material. This gave us really high advantage in the sense that we have nanoscale surfaces, which are empathy, which are accessible very nicely. And these networks, we can change the porosity, means we are able to control the surface accessibility, and at the same time they are very simple to choose. You can use in the hand, and you have got lot of flexibility to use the nanomaterials in the daily life, starting from, say, electronics, sensor, composite engineering, and many other directions. So this, starting from almost very nanoscale particles to wires, and then to tetrapods, and then to use the self-assembly feature, I could reach to a place, reach to a kind of certain stage where I can make a really sponge-like material out of ceramics, a flexible ceramics. You can bend a ceramic out of zinc oxide, and then you have multiple functionalities. Even why do we say smart in that sense? Because here you can apply, so you can apply the stress, and then what is happening, that we are kind of changing the distance between the arms in a real time. And if we think from quantum mechanics point of view, if you put a light on such a material, then the light is going to be scattered. And basically we can, by applying kind of tensile or compressive stresses, we have the possibility to tune a kind of the scattering behavior and the pattern, because there are a lot of kind of scattering paths available for light to get scattered. So that's how we say, from a very simple to very advanced material, and in the same material system, we have all the flexibilities.
So Yogendra, I was just wondering then, what applications does that enable? We'll dive into them later on, but this, the smart material application of light for scattering, what properties come from that for this tetrapod structure, and then where can it be used as a result of these properties?
Yeah, so these tetrapods structure basically the self-assembly nature, which is offering a kind of random degree of porosity. And this is a much preferred geometry because of several reasons. I mean, the idea comes from the coastal areas. When you are walking along the water side, along the sea, where there are high waves, and these ceramic tetrapod building blocks are mounted next to the water to reduce the water drag from the water, and because they form an very efficient construction to reduce the wave because of the random degree of porosity. The same way, here, these networks, we have the possibility to change the scattering pattern of the light. For example, if we have the possibility to use the zinc oxide feature, optical features, and together with the scattering path length, we can convert even the coherent light, so say a laser light, into a normal light. So imagine 40-50 years before, we had light bulbs. Now light bulbs are not part of our homes. They have gone to the museum. And now we have all over LEDs, but it could happen in future that LEDs are also following the path of light bulbs, and we are going to have laser-based lights in our homes, simply because they need much less power and they have very high quality light. Very high quality. Actually, the main question is how to degrade the quality of light, and where such kind of a sponge could be very, very helpful. Imagine often it does happen that in the hospitals, we are a patient is sleeping, and during the sleeping, everybody is making different kind of movements, and we are definitely interested in those movements. And what could be that if we design such a bed as such a sensor bed for the patients or the normal person, and whenever the person is making a movement, imagine if this kind of these movements are recorded into the real-time three-dimensional space, then you have a pattern into the morning with respect to the time, and we know how the movements have been. This might be helpful in kind of treating certain treatments for certain diseases of the patients. So these are some which are visionary applications. And apart from that, we are using these kind of networks as sensing gases, UV light, different volatile gases, including recently we were using them to kind of put into the mask to kind of monitor the real-time interaction with pathogens or whatever. When you walk, you are exposed with a lot of pathogens, gases, bacteria, whatever into the environment, and we are making an event, if it is possible, to mount on the mask and to control it with the electronics and to get some information of the exposure that might help us a lot. So say intelligent mask, since COVID, it is a very much need we are working on. So these are some advanced aspects we are working on.
One thing you mentioned earlier was that these smart materials, usually at nanoscale, are hard to mass produce. How is zinc oxide's ability to scale to fit like a bunch of really cool everyday applications such as the light bulb? How can we utilize nanoparticles that are easily formable but have to be scaled to get to the point where everybody could have it?
Yeah, this is a very good question. Thank you very much. Often, if you go to the nanoscientists, anybody you go in a daily life and ask a nanoscientist, you will see very nice results, very good performance, very good device, and everything. But what if you ask that, do you want to buy 1 kilogram of this nanomaterial? I'm quite sure you are not going to get the answer yes, maybe one day or maybe 1 month or 1 year. But here, that's the beauty of our kind of approach and our smart materials research, that we could develop a process which is a very simple process in the ceramic. In the ceramic crucible, we take a precursor material, which is zinc particle, and mix with a polymer, white powder, and this is in 1:2 ratio. This directly is going mounted into the furnace. Furnace is heated, and after say 900 degrees centigrade, the temperature remains constant, and after 1 hour, the kind of crucible is filled with white powder, which is tetrapod basically. So this process is so simple that we are able to produce these tetrapods in large quantities, and we have been able to produce several kilograms up to now. And this process has been going on since last 12 years. So in this respect, we are very, very happy about that. Nano from lab to life is a really important question. In the lab, everything works perfectly, but when we go to the life, what if? And there, we are happy that we are able to move from lab to life in a very good way. And there, still, if you will ask me for 1 ton, then I would answer in the same way like normal nanoscientists, but at least we are kind of able to take promises in kilograms.
That's really cool, especially when you talk about scaling. That's such an easy process. So now that you've kind of laid it all out, let's dive into an application you talked about. So in some of your papers and patents, you reference using these smart materials for biomedical applications, which can bind to viruses. Could you talk about how this works and why we would want to catch these viruses, and then what we could do once we catch these viruses?
Well, that is something which is very, very remarkable, and that is very, very interesting. We were meeting with a professor at conference. He is a virologist from University of Illinois at Chicago, and it's just as when you meet two people in anywhere, you start talking from nothing to something. So then it happened that I told, yeah, I'm able to grow these nice tetrapods from zinc oxide, and he had seen some papers where nanoparticles were found to be against viruses. So some antiviral effect from gold nanoparticles was reported. And then he had just asked arbitrarily, okay, Yogendra, you are making these new particles, tetrapods. why don't we kind of work together? I would really like to investigate if they have something to do against viruses. And then, yes, very fine, because as a material scientist, we are always kind of motivated to find more dimensions of our material in application areas. So I was sending the tetrapods, and after 6 months, we got our first result about that these tetrapods have the ability to bind the viruses. And this works in a very simple way. Imagine in a petri dish, you have normal cells, you have viruses, and typically how is it done? That they put certain number of viruses and then they try to monitor how many live cells are there, how many cells are dying, and they monitor the density of viruses. Imagine in the same way, in the same petri dish, we put our tetrapods as well. So what was happening after putting the tetrapods? Some viruses, I'm talking about herpes simplex virus 1, which comes on our face, it goes away. And then kind of what was happening, so virus is around 100 nanometer, and this is around 1 micron, this is even lesser, say 100 to 200, 400 nanometer. Then easily, because of this structure of the zinc oxide 1D and the oxygen vacancies, these viruses are bound on the surface. And that's where the story was started. Then we tried to understand the mechanism, and that was true because there is a property called band gap of the material. The zinc oxide has a band gap of 3.37 electron volt. Means if you take a UV lamp on it, then you can make more oxygen vacancies, and that was confirming that more binding of viruses. And this was really a great motivation for us to go in the direction of biomedical engineering. That's why I say from nowhere to somewhere. And then, of course, the questions up to this point, being a physicist from physics background, I knew that probably there is only one type of virus exists in whole universe. Now, after 2022, even virologists do not know how many viruses can exist into the nature. That is the scenario. So, well, to make kind of a story short, we studied about different viruses, but of course, one question we should ask ourselves for any new material, what about its cytotoxicity? Means if my material is killing the healthy cells or not, and if it is killing, then how much, low or high? Every material is cytotoxic, it's a matter of high or low. But we found due to this large size, this material is low cytotoxic. So that gave us a really huge window. We get super high motivation to go into the biomedical engineering. And we have done animal studies. We have seen successful results. Not only the tetrapods bind the viruses, they are also able to neutralize the viruses by helping a cell kind of triggering signal to WBCs. And not only this, there is always, when you put a material into the liquid system, always there is a release of ions, and zinc ions are very, very helpful for, as they are known as the cell growth promoters. So the cell growth is much faster. So in the overall, the structure, shape, and plus the zinc oxide properties were very, very helpful against antiviral applications. And we are very happy we have launched already a product into the market called Affinovir. One can buy from Germany. It is a cream and it can be used for antiviral treatment. It can be used for any kind of antiviral treatment on the surface. So since then, we have been doing research into the biomedical direction. We have designed advanced band-aids to treat the kind of wound healing. We have designed membranes which are suppressing the bacterial growth into the root canal. So I would say not from the biological background, not from biomedical background, we started from scratch, but we have been very, very successful in this direction.
That is incredible. And it's crazy that there's a product already in the field. So first of all, congratulations. And second of all,
Thank you very much.
I was just wondering, can you help me fill in the gaps with so how exactly does this material, how do the viruses develop an affinity to kind of latch on or bind to this tetrapod structure? I know you mentioned the band gap, but I was just wondering if you can kind of fill in those details there. Yeah, I was just wondering kind of exactly
Yeah.
what about this structure creates that affinity.
Exactly. Basically, we are talking about, so when I'm talking about viruses, it is herpes simplex virus 1. And herpes simplex virus 1 is the enveloped virus. And this envelope is made out of certain chemicals. In this case, it is heparan sulfate, which is negatively charged. And the doesn't matter whatever you do, this is a material property, zinc oxide material. Always you have certain oxygen vacancies, and those oxygen vacancies are positively charged. So there is just some certain kind of electrostatic attraction. So what is happening in the cell culture medium, if viruses are passing by and they come into the close vicinity to the tetrapod surface, zinc oxide surface, then they are getting bound. And what is also happening that this structure, if you see the like stairs in your home, when you go from bottom to top, there are a lot of stairs, and these are good places where if virus could feel little attraction, they go and then they sit over there nicely. And this function, this behavior from these tetrapods enhances if we put more UV light on it, then more vacancies and then more binding. This happens. And the other way around, the neutralization aspect is very, very interesting. They are not just neutralizing because of the material properties. Basically, here we have zinc release from the structures. And what is happening when there's this zinc release, probably you know now after corona that zinc ions are very, very important for our human body. They control nearly 200 enzymatic reactions in our body. They control metabolism. They are the one who are responsible for immune boosters. So people were eating zinc rich tablets to enhance their immune, to protect themselves against corona. So what is happening that the zinc release into the local environment is creating a kind of gradient, which is helping a kind of cell signaling. The WBCs, which are really the kind of soldiers in our body, they go and they grab the viruses. So the viral infection, there is always a kind of fight between the WBCs and the viruses in our body. When WBCs count goes low, then the viral infection predominates and it's other way around. So that's why if our immune is kind of strong enough, then we are safe against viruses. And that's how it works basically.
Wow. Yeah, that was super insightful.
Yeah, and then over the time we have learned as a kind of physicist, so what we have learned that zinc oxide material is antiviral, antifungal, antibacterial, anti-cancerous, and antimicrobial. I'm quite sure many more things are going to come on board. So in this case, it is going to be a most important biomedical material in a lot of kind of treatments.
Wow. Yeah, and so now let's transition to another very unique application. And I know we mentioned kind of the band gap and how, and I know that can be used in the electronic applications. And so I was wondering if you could touch on past uses of these zinc oxide tetrapods and how it can be potentially applied to flexible electronics.
Yeah, so when we talk about suppose making a sensor based on the nanoscale materials, so either we take a nanowire, but then first we have to make a nanowire, then we have to go and put in between the two electrodes, mount with the clean room. There is a complicated process, and nanowire is always lying on the base, this sensing element, and we do not have the full surface accessibility. So there are a lot of challenges. And it's the same holds for the thin film as well. But here we came up with this idea that yes, we could design a very thin slab. As suppose this is the sensor element, for example, if we make our sensor element out of kind of nanostructures, this could be a sensor element. We can easily connect the two ends in a very nice way. And then what happens if there is anything coming, it is a porous material, so we have much more exposure, and then we can easily measure the response. And in this way, this is also kind of flexible. So what we started doing, we came up with the idea that we prepare a thin slab of this tetrapod network, a long slab, which we use as a sensing element. Very easily we can mount this into the two electrodes. We can connect it to the voltage supply and measure the current. And this was then used as a UV sensor or a gas sensor in a very good and very efficient way. And in the same way, so this has been very well established. For example, different types of UV sensing, gas sensing, VOC sensing. Often there is a question that what about the selectivity? If in the lab, my sensor works perfectly, I measure, but I know which gas I am putting on it, so we understand very well. But what if I take the same sensor to the airport? Can the sensor tell which gas it is sensing? It's not straightforward. So the selectivity is very, very important. And often one material is not enough. One material is not sufficient with respect to every gases. Every material has certain properties. But with this slab, we have an advantage that we could also put a selective molecule. It could be marker, it could be other nanoparticles or whatever. Then we can use this bridge as a sensing element, but then more functionalized with the external element for the selectivity point of view. So here we have multifunctionality on the board and on board actually, and this bridge is kind of flexible too. So in that way, the flexible sensor could be designed. Why we call them smart is also very, very kind of special with the zinc oxide, because if you try to bend, I mean, 1D structures can be easily bent. Imagine if you try to bend a glass rod in your kitchen, it will break down, you will not be happy. But if you take a glass fiber, you can put and fold it into the pocket, whatever you want. So that's how, say, 1D flexibility. If our hair is 1 centimeter thick, forget about bending, but it is few micron, you can easily bend it. In the same way, so these nanostructures from zinc oxide, you can 1D structures, one can easily bend. And with zinc oxide, it has a special crystal structure, how these atoms arrange themselves into the lattice, and it is a technical term called non-centrosymmetric structure. So that means if you bend it, then the bonds are aligning in a different manner, which they generate a potential across it. We call them piezo potential. And in this way, the sensor element could also power the sensor itself. So in that way, it could be a smart sensor. So now we are trying to integrate this bridge into the mask directly for monitoring the biological identities, molecules, whatever. But that is at the preliminary stage.
So yeah, the last thing you mentioned was piezoelectricity, and so that was where my mind was going. One question I had is that these non-centrosymmetric materials have different piezoelectric responses, basically how strong the electronic response is to force. How does that compare to like other very common ones? Like I think LAB6, I think, is a common one. Or
basically you go, so it's always kind of the dielectric constant or is the most important thing, and basically the value is very important. So BaTiO3 is the best material in terms of piezoelectric coefficient value. So if you compare the piezoelectric coefficient values, then I would choose BaTiO3. However, with BATIO3, it is difficult to achieve 1D structures and the tetrapods. So far, nobody has done. We are trying to do it. But with zinc oxide, we have easily the possibility to make these porous porous bridges as a kind of nano elements. So in that way, we have win-win situation. But for certain applications where we are looking for very high piezoelectric coefficient, then we in certain polymers, these BATIO3 nanoparticles are embedded in this way. But mainly zinc oxide is, if we talk about 1D piezoelectrics, then it's zinc oxide, which is very, very popular. It depends upon the choice of application and the context where you want to use in. So every material has different plus and minus. And according to, as per our need, we have to decide what we really want.
And so I think you've explained a lot of different applications and their uses, and it's very flexible almost to how it could be applied. One question that we had was, can you use the same tetrapod formulation or the structure on different material systems, and would that unleash like a whole like range of new applications?
Yeah, basically we started with tetrapods, and then we have been so successful because we harvest here the material properties plus 3D shape. So the combinations, the shape plus properties combination makes them much better. And this is kind of, we have done a lot of composite engineering. For example, even we could design the composites which are able to tell if there is any internal damage propagating by a color change. So we have been very, very successful. And in that case, this is a simple curiosity coming. Can we make tetrapods from other materials like metals, metal oxides, carbon, polymer, hydrogels, whatever, using the same approach? The answer is no, because it is the material which decides how it wants to grow. We cannot control materials, its crystalline structure, its vapor pressure conditions, temperature, and several other factors. However, we learned from some experiments that zinc oxide is mechanically very strong, physically very robust material with several gigapascals, up to 200 gigapascals of Young's modulus, very strong, but chemically it is a poor material. If you put into, for example, acetic acid, you have in your kitchen, the material will melt away, it will behave like a salt, basically. So then this gave us really a very nice idea that I could deposit something on the top, and then I could chemically remove the underneath backbone. And this was really a new thing. We started nearly 10 years ago, and now we have really a large family of material, starting from carbon, hydrogel, polymer, nitrites, oxides, silicon, and many more classes of tetrapodal material. So in fact, we have developed many different tetrapods, and since the underneath has been removed, now it is hollow in nature, and we have developed tetrapodal materials from various materials. And the advantage is now still you can put really functions on the top because of the size and the shape. This gives you much more flexibility to put more functions on the top, making them more smart in terms of properties and accessing those properties. That's how we define our smart material. And there we have been very, very successful, and we are very, very happy about it. So always we tried to grow 3D tetrapodal diamond structure, and we were successful. So there are a lot of things which are going to come in this direction. This research was starting from a very basic research, but now it has added many more amplitudes in the direction of materials engineering. So we are simply going with this approach: new materials, new shape, new form, new combinations, new fundamental properties, and many applications.
That's awesome. Can you paint a picture for us for what your vision is for like how this newfound tetrapod engineering with different material systems, what that unlocks for us, maybe like 10 years from now, what kind of applications can we see these structures being used in?
Yeah, basically you will probably see in your home as a lightning application. You will see into the mask as a kind of a smart sensors, for example, intelligent mask, one could be, and something what we are developing now, that to develop advanced catalytic material to convert, say, CO2 into sustainable fuels, say methanol or whatever. So it could happen that kind of you see the base technologies, tetrapod-based networks are technologies which are used into kind of reducing CO2 emission from our environment and creating fuels out of it. Or don't wonder if you see some tetrapod-based filters in the for filtering water or filtering several bacteria from certain liquids or chemical separations. So there are many applications going to come on board. I can't imagine the scope actually. It's very broad.
Wow, that's great that it can be applied to so much, and hopefully we'll see it soon. I guess just to wrap up the conversation, you have had quite the illustrious research career, and so we want to know, what advice would you give to young researchers or people who are trying to get into the R&D field about how you first like go on such a long journey, but just continually produce like very high quality research?
Yeah, basically the research. So there should be a self-motivation that I want to do something and I want to do something new. And all the new ideas are always coming from our daily life. When we walk into the forest, when we go to run, when we swim, when we walk into the kitchen, or when we are driving the car, or when we are hiking into the mountains. We get ideas always from the nature because that is the kind of biggest thing we have all around. And I always try to learn whatever knowledge, whatever informations, whatever ideas nature is doing, playing around us. I try to learn those something and try to implement what I am doing into the lab. So there is one-to-one correspondence, and this will always give anyone a new direction to keep on working, and this will fulfill your aims, this will satisfy you, you will feel as a young that this is something new, this is something novel, and you will always get a way to go ahead, go forward. So always I try to correlate the things from the daily life to the things into the lab in one-to-one correspondence, and that is giving a very nice motivation. When you go to, for example, for me, it was a good motivation when I was walking along the coastal areas in Mumbai, where we saw a lot of architecture from the Tetrapod. And then, of course, when I was watching a movie into the theater, then I could see that the popcorns in the bucket, they are able to arrange themselves. So always, as a young students, colleague entering into the field, try to take a problem, think about it, something from the nature, how nature is arranging, how things are looking like, and this will give you a way back and forth. Yes, I could do this. If I could do this, then it will be like this. And this will tell you the way how to go ahead.
I love that. Thank you so much, Yogendra, for joining us today. That was a very insightful discussion, and I learned a lot about your tetrapod structures, smart materials, and I'm excited to see the impact it'll make all around us.
Yeah, thank you very much. It was very pleasure and honor, and I'm very much excited for more podcasts.
Absolutely. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.